Hello everyone. So in this video, I want to cover the design of anti-reflection coating, and primarily I would be focusing on the quarter wave optical thickness design for single layer as well as double layer anti-reflection coating, or short for ARC. So initially, the material that we selected to design the ARC is for a photovoltaic terrestrial application, which basically implies a silicon PV cell uh, having the wavelength range of 400 to 1100 nanometer um, design range. So, and it is also considered as a bulk infinitely thick layer of silicon and having a constant refractive index of 3.9. Whereas the other medium is considered to be an air, and based on these two medium of silicon and the air, we would design our single layer as well as double layer anti-reflection coating for both the quarter wave optical thickness design as well as non-quarter wave optical thickness design. So initially, we did some scientific literature survey as to see what kind of designs are already available for ARCs. And these materials right here, silicon oxide, tantalum pentaoxide, are primarily used within the single layer ARC, whereas magnesium fluoride and zinc sulfate are mostly used in double layer ARC. So we employed these material as well, but the rest of the calculations and related to the second material and their thickness as well as their refractive index was done by mathematical approach as well as experimental approach. So let us start first with the um, okay. So before we start, I just want to cover this particular AM 1.5 global reflectivity spectrum that you see. So essentially, the anti-reflection coating that we will design would be compared to AM 1.5G spectrum that you are seeing here. Because we are considering terrestrial application, so we are selecting AM 1.5 instead of AM 0, which is apparently for the space. And our design, the design wavelength that we have chosen for our purpose is around 500 nanometer. So for all the design that we would consider in this analysis would be for 500 nanometer and AM 1.5G. Okay, so moving on, the first one, the first analysis is done without any ARC, and for a normal incidence, as well as a theta equals to 30-degree incidence on a photovoltaic um, cell or a plate. And then using simple analysis, we find the reflectivity to be around 35% for the photovoltaic silicon, having the refractive index of 3.9, and the second one being the refractive index of air being 1, right? And again, for normal incidence, we can use this particular formula that you are seeing on the screen right here, and the reflectivity turned out to be 35%. Whereas if we are talking about angled incidence, for example, at 30, theta equals to 30-degree, then we would have to find the S and P components separately, as you are seeing here. So essentially, we have these two expressions to define the S wave as well as the P wave, or TM or TE wave, and then we plotted the reflectivity spectrum of both the waves individually, as you see here. You can see that at around the angle critical angle of about 75 degrees, we have the TM wave going to TM reflectivity going to 0, which is essentially the critical angle, and for which the TM wave would become 0, or the P wave would become 0. And as you can see, if we increase the angle of incidence, the reflectivity tends to increase until it becomes 100% right here for the completely normal incidence of 90 degrees. Right, so this particular analysis was without any ARC, and in the following designs we would design ARC and then we would perform the analysis. As for this particular chart that you are seeing on the screen, this is its corresponding MATLAB code that you can use. As you can see, we have written the refractive index for both mediums, and then we use the reflectivity formula for the normal incidence, and this particular chain of reflection is for the angle incidence. These are essentially the same model that are present right here. These two right here. right? And if we run this particular section, you can see that right here. So you can see the plot that we saw earlier. As we continue to increase the angle of incidence, the reflectivity for both the S wave as well as P wave would tend to increase. Right, moving on to the second design, which is of a single layer anti-reflection coating for a normal incidence. We have to find the refractive index of our desired anti-reflection coating, and for that purpose we multiply the refractive index for both the mediums and take the square root of it, and it turned out to be 1.975. So essentially the refractive index of the anti-reflection coating that we need had to be 1.975, and since it's a quarter wave design, so the thickness of that anti-reflection coating would be the base wavelength that we have selected, which is 500 nanometer, divided by 4 times the refractive index of ARC, which turned out to be 63.3 nanometer. So for this purpose, we did a bit of survey as to which is the closest material that we can select in order to which has similar refractive index as this one. So we found out that tantalum pentoxide is basically a very close material to our design, offering the refractive index of 2.1587 at the a wavelength of 500 nanometer, and similarly, therefore we basically use this particular material, tantalum pentoxide, for our design as well. Once we had that, we can simplify the reflectivity by using this material in following the transmission line theory, which states that we can find the reflectivity on the within the first medium by basically first finding the reflection in the second medium, and then the positive reflection in the first medium, and the characteristic impedance as seen by the first medium, followed by the negative impedance negative reflection as seen by the first medium, and finally the reflectivity that is seen by the first medium. So this is essentially what's modeled here. If you see in the right here, okay, this one right here. So essentially these equations are modeled for single layer ideal anti-reflection coating for quarter wave optical thickness design. And as you can see, we first find the gamma p, then gamma a positive, then the impedance in a, and then the gamma a negative. Right, and all of this, the rest of this is related to the refractive refractive index of the various design material that we used, their characteristic impedances, and then we have this AM 1.5G table or data that was already available, and it's taken from the internet. And then we have the wave numbers calculation right here. Then corresponding to the wave number, we have so these two are for the contour design of non-quarter wave optical thicknesses, and these are the quarter wave optical thicknesses right here for various layers that we have chosen. And the rest of the code basically deals with the equation that I've with this transmission line theory that I've explained here. So if we talk about the results of the first one, we can clearly see that for a single layer optical thickness design for non-ARC, yeah, as we saw previously, it was 35%. But if we like zoom into this particular region right here at 500 nanometer, we can clearly see that for ideal single layer quarter wave optical thickness design, the reflectivity is zero basically, which is our desired result. But in real life, since we don't have an ideal material, instead use tantalum pentoxide, so you can see there is some reflectivity that is being offered by this real material compared to the ideal material for single layer optical thickness design. But it should be noted that the margin for the reflectivity is quite narrow, and only at 500 nanometer does it go to exactly zero. Okay, so this is the code followed by the second design.